So I want to cover two related topics in this hour. So one of them is how you extend this model. If you don't use equilibrium assumption, what other models can you use? The second, and I alluded to this yesterday, LES has this unique feature that you can build model parameters, or you can get the model parameters during the simulation. You can back it out from the simulation, which is very useful overall. So we want to look at both of them, okay? So, oh, I have to switch this. All right. So I want to step back a little bit, go back to the PDF part of it again, just to illustrate this notion of building model parameters from within the simulation, okay? So which is called the dynamic procedure. It's very unique to LES. There's not a, I don't know of any other simulation tools where you can do something like this. So essentially what you do is that you run the simulation, and as part of the solution, you have a lot of data because this is a three-dimensional simulation, it's time varying. And from the simulation, you can actually extract models which you can now plug it into the simulation, right? So this is why it's called the dynamic procedure. Now, before all of this happened, there was the Reynolds average Navier-Stokes equations, which was the most common way to simulate any kind of flame. And one of the fundamental problems in using RANs was that there were a lot of model coefficients. You know, I don't know if any of you have used RANs or still use RANs. There's this dreaded K epsilon equation. I don't know if you've heard of it. So this equation is at once the best thing for engineering, and also it's a demon to be mastered. So it has these multiple coefficients in the equations, C epsilon 1 and C epsilon. I know this because this is what I did for my PhD also. So C epsilon 1 and C epsilon 2. These are two parameters. No one tells you what this value needs to be. It could be 0.6 or 452, right? No one knows. And depending on what you fit, you can get very different results. You can get a jet that's 10 millimeter tall or 2 meters tall, right? So it will change. So this was a big problem. And one of the reasons you cannot trust the RANS calculations was because it was so sensitive to these model parameters. So when LES became popular, its biggest achievement, and this comes from a 1991 paper by Parviz Moin, along with a few others, this idea known as dynamic procedure. So you take the solution, and from which you can actually figure out what those model coefficients have to be, okay? And so you don't have to tune anything. You just set the mesh, you specify the boundary conditions, and you run it, and you get what you get. If you don't like what you get, then so be it. That's it, yeah? Which is very different from the RANS approaches. So this is something, it's good to know how we do this. So there are many places where this dynamic procedure can be used. I want to use this for, I don't know what's happening here. I want to use this for this PDF, right? Part of the PDF, because we've been talking about this. So you can learn it in this context. People use it for many different aspects of modeling. So there's a particular kind of requirement for being able to use dynamic model. Once you satisfy it, you can use it for any method. So we have the G of Z, which is the combustion model, and the PDF of Z, which we need to somehow specify. And I told you there are many ways to do this. Some people make it more complicated, others are more simple. The simplest way to say what the PDF is to prescribe a functional form. You say that the PDF is a beta function, not a Gaussian function, but it's a modified gamma function. Okay, so that's the beta function. And the beta function depends on the average value, Z filtered value, and a second quantity called Z filter bar squared. You see at the bottom of A, you see that quantity, Z prime squared filtered, yeah, tilde on top of it. So that is called scalar variance. So you take a box, you take the average, that gives you Z filter. If you take the standard deviation or the variance of the same box, that is your quantity Z prime squared tilde. Okay? So it's just moments of the PDF. So if you know the first two moments of a PDF, you can prescribe a functional form, then you have fully specified the PDF. Okay? This is not true for every PDF. It's true for a class of PDFs that we have. So all you need to know is the mean and the filtered function. Okay? So again, going back to the same picture I showed you before, if you take DNS data, you compare it, that kind of fitting seems to work really well. Okay? So once I have this PDF, the way I will solve any problem is I'll solve this filtered transport equation at the top, which is for mixer fraction. There are no chemical source terms, so I've gotten rid of that problem because I've rewritten mixer fraction in such a way that there is no chemical source term. I have mapped all the reactive scalars to mixer fraction, which means that the filtered values for y only depend on the mixer fraction filtered mean, Z filter, and this scalar variance. Okay? So if I know what scalar variance is in each box, it's done. I've solved the whole problem. Okay? So this is a complete loop. Okay? Now, people spend a lot of time figuring out how to solve the scalar variance and so on. So I don't want to go too much into the depth of the different ways to solve scalar variance. But what we need to understand is how you get this scalar variance. Okay? So there's a simple formula here, and this is identity. This is the identity used to specify what scalar variance is. You say Z prime squared, bar or tilde does not matter. I'm using this interchangeably. You take Z, you square it first, and then filter it. And then you filter Z and then square it. So the difference between these two is scalar variance. And that comes from statistics. You can show this, that this is statistically the right thing to do. Okay? This is how you compute variance of any distribution. You take the sample, you square it, you find the average. You first find the average and then square it, and the difference between the two is your scalar variance. So if you can specify the scalar variance at every point in the domain, in addition to the filtered mixer fraction, you can get all the species compositions immediately. Okay? So here we use this trick. And this is a very clever trick. When you do LES, and I showed you pictures of it yesterday, LES looks just like DNS, but it's a little bit coarse. It looks a little less turbulent. It's not as chaotic looking as turbulence is, or as DNS is, but it has a lot of different scales in it. So this is the energy spectrum. We discussed this yesterday, minus 5/3 slope here. I have a delta, which is my filter width, and that's this line right here. Now, of course, this is all imaginary, right? Because in a real flow, there's no sharp spectral cutoff. So it's not as clean as this. But for the purpose of theory, I'm assuming it's a sharp cutoff. So all the yellow region, I have no information on. So that's all the small scales, and I've filtered it out. So I somehow need to model it. So what I do is this. I have all of these scales in my simulation because I'm resolving all of these scales. So I go a little bit coarser, okay, up to delta hat. Now I physically filter the solution, the LES solution at every time step. Now I've removed all the scales below delta hat from the simulation, okay? And looking at what I have not accounted for, the difference, I can now predict what that yellow box is going to be. So by knowing what that purple box is, I can figure out what the yellow box is going to be. This is the whole game, okay? So as long as you have any quantity that has a spectrum that looks like this, where the small scales are less important than the larger scales, I can apply the dynamic procedure. In the dynamic procedure, I take the LES solution and I just filter it explicitly, and from that difference, I can figure out how to get the unresolved scales. And in doing this, I don't have to specify any model parameter. Now, the math of this is mind-numbing. So I don't want to, there are too many bars, hats, tildes, squares, primes, and everything you can imagine. So it's not learning friendly. So it takes a while to figure it out. But it's all in the slides, so you can take a look at it. The key additional thing you have to understand, if you have to use the dynamic procedure, you are trying to find a model coefficient, which is one variable, okay? To find that one variable, you need to have some equations. You need to have left-hand side is equal to variable times right-hand side, okay? So if you have like this, then you can divide one by the other, get that variable. So typically what we do is, we write the scalar variance in terms of two different models. That's what we do. So the model here is what is called the gradient-based model. So I say scalar variance is this coefficient CD times filter width square times the gradient of mixer fraction squared. So this is my model. Of course, if delta goes to 0, I do no filtering, that variance will become 0 because everything is resolved. There is no scalar variance. There's only one value for each cell. So once I have this, then I can go through a set of procedures to take the CD out, to compute the CD during the simulation, rather than saying its value should be 0.2 or 4 or whatever it is. Okay? So that procedure is given in this. I teach this in a class, and it takes me like about 1.5 hours to go through this. So I do not want to do this here. But I have the formula, but I'll show you how this thing looks. So this is my original solution. This is my filtered Z. I've solved the partial differential equation. It's some part of the whole geometry. I think it's a shear layer. I took it from this. So I have this section here. I specify an LES filter, which is the grid size. That's my LES filter. My test filter is about twice the size of the LES filter. Okay? And using the set of procedures, I can compute all of these quantities just from this solution. So what I do is I take the gradient and then square it. That's this guy. Or I can first test filter it and then take the gradient, which is this guy here. So all of this comes from just the top left solution. And if I go through the math, in the end what I'll find is that that CD coefficient I talked about, you can actually back out for every point in the domain. So it's not some constant value. It actually goes between 0 and 16, depending on where you are in the domain. So you can find this coefficient during the simulation. And once you find that coefficient, you plug it back into the model, you get your scalar variance, and once you get your scalar variance, the whole problem is closed. Okay? So this is a big achievement for any kind of simulation. Because you can extract the model coefficients, you do not have to specify them ahead of time. And if you want to do this for a jet flame or a bluff body flame or some cavity flame holder, each one, the model coefficient is going to be different based on the level of turbulence, the kind of flow structure, and so on. And you don't have to worry about those differences because this method is going to figure out how to extract the coefficient. Okay? So this is a big advantage of using LES methods. Okay? And I would say much of the initial excitement in using LES between early 90s and about the middle of 2000s is just from the fact that you are able to get these model coefficients. So it was vastly superior to RANS in that context. There are a lot of holes here also that need to be filled, but this was a big jump compared to technology that we had before. Okay, so this is for the subfilter variance or the dynamic procedure. So I want to go to the next step, which is to say, if Y is G of Z, what other models exist for this manifold relations? So far we looked only at equilibrium solution. Given a mixer fraction, I compute equilibrium solution, tabulate it, and use it. There are much more sophisticated models that you can use. So we'll go through a couple of them, trying to understand how this works, and then we should be good based on these manifold methods. So before that, you have to know one quantity. If you do combustion, you have to know what this is. Chi, which is the scalar dissipation rate. Okay, we talked yesterday about turbulence dissipation rate. This is the scalar dissipation rate. It's an Einstein notation, so when you have this repeated index, that means it's a summation. It's the gradient of x squared and gradient for y squared and gradient for z squared added up, right? So it's a summation of 3 components there. But that's the scalar dissipation rate. And what you're going to do is to use this variable in addition to mixer fraction to sort of quantify what happens to the flame when turbulence or other effects come into picture. Yeah, so we're going to use dissipation rate for this. So going back to this, we have this diffusion flame, and this is the schematic that we looked at. There's fuel on the left, it gets consumed, and then there's nothing left on the right. There's oxidizer, and then it's coming in from the outside, and then it gets consumed as it goes towards the wick. right? So this is the structure we're going to have. And the temperature reaches a peak in the middle. So if you take equilibrium solution, the main disadvantage is that if turbulence now tries to destroy the flame. So if you take this candle and you blow into the candle, at some point it's going to extinguish, right? Unless it's one of those magic candles. So it is going to extinguish. And the equilibrium solution does not allow this. It says that if you have fuel and oxidizer, you will always have equilibrium temperature there, okay? So it does not allow for strain applied to the flame to extinguish. So that model is deficient in that way. So we need a new model that takes into account the impact of strain, okay? So that's the main idea here. So we are not touching P of Z, the probability, it's all the same. What we are changing is G of C, the mapping between mixer fraction and the species, okay? And all of this are done in roughly the same way. What we do is we take some canonical flow that we are able to measure or study very easily using one-dimensional simulations, let's say. And we say the practical application that we have, let's say aircraft engines or jet flames or whatever it might be, are similar. It has a similar flame structure to this canonical flame. So if you have to do this kind of manifold-based method, you first have to identify an equivalent canonical flame, which has some characteristics that are similar to your final application, okay? So a counterflow diffusion flame is a good canonical configuration for this. So where you have two tubes, it's not clear at all from this picture. This looks like some nuclear reactor, but on the left there are essentially two pipes, okay, that are pointing at each other, and they're perfectly aligned. And there's fuel coming out from the bottom, oxidizer from the top. No reason for this configuration. You can turn it the other way around also. There could be fuel coming from the top, oxidizer, it doesn't matter at all. So when they meet in the middle, they're pushed out towards the side. So they all, the flow has to go somewhere. It goes through the side. And if I now measure the concentration along the axis, that will look like the diffusion flame that I showed you before. So fuel will be high here. As it goes towards the middle where the flame is located, let's say, it's going to go down in concentration. And of course, if you go all the way to the oxidizer outlet, there is no fuel there. So this structure is going to look exactly like the flame that I showed before. Yes? Do you have a question? Oh, okay, all right. Okay. Now, the advantage in this is that I can set the distance between. I cannot make it too far away. I can move them closer or move them far away, okay, to some level. But I have a velocity that I've specified. There's a velocity for the fuel, there's a velocity for the oxidizer. So if I take that difference in velocity, so there's some delta U, okay, in velocities, and depending on how close they are or how far away they are, there's a gradient in velocity. So there's delta U by delta X, the distance between the two ports. The delta U by delta X, if you look at the units for it, is 1/2, right? So that looks like strain rate. So it looks like strain rate. So by changing the speed or the separation between the two tubes, I can change the strain that's being imposed on the flame. So now I've added a new parameter. Just like blowing into the candle flame, I can increase the strain by bringing the two tubes too close to one another. Okay? So now I can get many different solutions, flame structures, for many different strain rates that I can introduce. Okay, so this is the main advantage here. So I have a picture here, I think, of this. So on the left-hand side, mixer fraction on the x-axis, temperature measured along that one-dimensional line going from the fuel to the oxidizer. Of course, when mixer fraction is 0, that's oxidizer. When mixer fraction is 1, it'll be fuel. It has been cut off at 0.5 because nothing happens after that. It's all linear, so there's no information there. So you see here, there is this quantity called A, which is in 100 per second, which is strain rate. So it's per second power minus 1. Yeah? And you can make it go from 100, 1,000, 10,000, things like this. There's also the equilibrium solution, okay, which sits here. So now, Equilibrium solution is what we saw before. It cares nothing about strain. It's always the same value. Okay? But the moment you change the location of those ports, you can start getting these other curves. So when A is 100, you see that it's very close to the equilibrium solution. There's some changes, but it's really close to the equilibrium solution. But when you go to A of 1,000, that peak temperature drops because the strain is trying to reduce that stoichiometric, the reaction at the stoichiometric surface. So it's going down. The reaction intensity is going down. And when you go to A of 10,000, it's gone down substantially, right? So from a peak of about 2,200 Kelvin, you've come all the way down to 1,400 Kelvin or so. So if you keep increasing strain, at some point, the temperature will become so low that the flame cannot be sustained anymore. It will blow out. So now you have a parameter, A, which if you vary, you can go all the way from equilibrium solution on one side to extinction on the other side. And when you solve the problem, when you solve for mixer fraction, at any given location, now you can have a map that's a little different. It's not just y is g of z. You can have y is g of z comma a, for instance. So you can compute the local strain rate using velocity field. And now you have two variables to map the solution. Now it takes into account strain effects in your model. So the same manifold model, now it's a little bit more detailed than what you had before, right? So that's what you have. And in fact, in this axis is a slightly different one. You take all the peak values, and that's this curve, and plot it as a function of strain rate, which is the different A values. And what you see is that it goes from very high values all the way to 1,800, and at some point it's just going to extinguish. It's a very famous curve. This is what will lead to what is called the S curve, used for manifold methods, but not critical here. That's not what we are interested in right now. But you see this temperature dropping as the strain rate keeps increasing. Okay, so now what I do is this. I say my Y, the species concentrations, are based on a new model G, which depends on mixer fraction and what I call as chi stoichiometric. Not strain rate, but chi, the scalar dissipation rate, evaluated at stoichiometric condition. Okay? And I'll tell you why this comes into picture. So this is easier to characterize from a flamelet table. That's why we have it here. And there's a relation on how these things work overall. So for instance, if I take along this axis mixer fraction and I compute dissipation rate, which is 2 times d times mixer fraction gradient squared. And there's only one direction here. So what I'll find is that I can plot this chi, and this chi will, so mixer fraction looks like this, okay? So it goes from value of -5 here, it's at 1, and then all the way it goes down to 0 at the other end, at the other port. If I plot chi of z, I'll see that it is 0, nearly 0, far away from where the two streams meet because mixer fraction is not changing. And same way it's 0 very close to the oxidizer port. In the middle, it has this form that looks like this. It's chi of, it varies based on what your mixer fraction gradient is. Now, of course, if you bring the two ports together, that mixer fraction is going to change very rapidly. So it'll be 1 all the time. Suddenly it'll become 0 and go to the other value. So this curve will become thinner and thinner and more and taller as the strain rate keeps increasing. So you have a relation between dissipation rate and this stoichiometric dissipation rate, which is essentially the dissipation you have at the flame surface. So if the flame is located here, that's the dissipation rate at the flame surface. So it's just a way to parameterize it. Then comes a math to figure out how to account for it. But essentially, once you have the model to say it's a function of both mixer fraction and dissipation rate, that's the new manifold that you do. Okay? So now you have two manifold variables. You have mixer fraction and you have dissipation rate, which means you need the PDF in 2 dimensions. So that's this guy right here. So you have to make some assumptions about how you model the PDF. So you write them as mutually independent, model the mixer fraction PDF using the beta function, mean value, scalar variance, and the dissipation rate using a delta function. So these details are not that significant for our discussion. Okay, and this gives you some models for how you will describe dissipation rates itself. So how does this look? So if I have, so the same table that I had before, I have mixer fraction on the x-axis. I varied chi because I varied strain rate, and I'm plotting temperature here. So for different strain rates or different dissipation rates, I'm going to get different curves here. And this whole table, instead of one equilibrium solution, now has a range of solutions. So I can blow this up very close to where the changes are happening, and you see that the mean temperature changes quite a bit based on what your dissipation rate looks like. So this adds complexity to the original equilibrium model. Now it depends on the local strain rate, how these variables will actually change. Now, this seems like a very subtle change, but it leads to really important results. So for instance, this burner was very popular in the 90s. So this is one of those configurations, experiments, that everyone will try to simulate, but it will never work out. This is, you'll get really bad results. You have to tune models, and if you tune models, you can get sometimes it works, sometimes it doesn't work, and so on. And the main reason, and I showed this yesterday also, this particular flame has this property that once in a while, the recirculation zones it forms, they are destroyed, and the flame forms itself again. So it's a very unsteady process. So if you don't capture that unsteadiness, then you don't get any accurate results. So what we find is that, and I showed these simulations or these movies before, if you add all the models I talked about right now, then you get results that look like this. So the dots there are from experiments of turbulent flames, and the lines are from the simulations that we did. So if you use these more extended manifold methods, you can get very close to what the experimental data tells you, which is very rare. Like if you do Rance methods, the error would be like 30–40% at different locations. So that comparison comes only from the dynamic procedure and from this extended model that you have. Now, after this, everything else that comes is just more and more sophistication. It does not change the basic philosophy. There are only 3 ingredients. You first need to figure out what is your canonical configuration to build that map, G. What variables are you going to include in that map? Mixer fraction, strain rate, dissipation rate, whatever it might be. And once you have these 2, you need the PDF, the joint PDF for the manifold variables. So 3 steps. And every problem, every method that you use always has the exact 3 steps. So I'll give you a couple of examples. This is the flamelet progress variable approach. So this is the extension of what I just showed you. It does something a little bit more here. So we found out that if you have extinction, locally if the flame extinguishes and comes back up, there's no way to describe using that strain model that we had. So this fixes that problem. So it's called the flamelet progress variable approach. It's very popular. It's pretty much routinely used for most aircraft calculations. This is a good technique to use. So what we do is we take progress variable C, which is the sum of mass fraction of H2O and CO. H2O is the full product of combustion. CO is an intermediate product. So if you don't go to completion, you'll produce CO. If combustion goes to completion, you'll produce CO2. Yeah? And H2O is the marker for completion. So you add those 2 mass fractions, that's your definition for reaction progress variable. Then you get an equation that looks like this. Now there's a problem, right? Because this contains a source term, and we did all of this so that we can get rid of a source term. So there's a very clever solution which Charles Peirce came up with. So the idea is that you take this progress variable and you write your manifold method, the mass fractions, to be a function of Z and C, the mixer fraction and progress variable. So now because you have constructed all of the reaction variables, you can find that source term exactly. You don't need to do any approximations. You can directly back it out from the manifold itself. Okay? So that S of C can be obtained directly from the solution. You don't need to model it explicitly. So this is the main advantage here. So I'll show you how this table looks. This is from a different simulation. So what we do is we take the same counterflow configuration. We write many different chi values, different strain rates. We generate all of these different lines. Okay? On each one of those lines, there's a particular mixer fraction, particular C value, the sum of H2O and CO. Okay? So we take that information and recast it. What you see on the right-hand side is the same table, but now written in terms of Y, which is your reaction progress variable, and Z, which is your mixer fraction. So you take a bunch of flamelet solutions, you recast them, and then you get your FPVA table. Now this is your manifold. It's a function of Y and Z, no dissipation rate anymore. It's mixer fraction and reaction progress variable, and then you solve all your LES equations based on these two variables. And I think that's what this tells you. Okay? Now you can keep adding more and more extensions to this. So equilibrium solution does not account for strain rate. Flamelet solution accounts for strain rate, but it cannot figure out when extinction and reignition can happen. So that's what FPVA fixes. But FPVA cannot account for heat loss to the walls or other kinds of heat addition, like a spark source, things like this. So it's adiabatic, so it cannot handle non-adiabatic solutions. So this extension fixes that problem, right? So from equilibrium to flamelet to FPVA to this extended FPVA accounts for enthalpy changes. So that's the main difference. There are many variations of this. I think what we have, because it's easy for me to find, it's my model. Doesn't mean that it's better or worse. It's just what's easy for me to find. So I'll show you an example of where we use it. This was a project from FAA for alternative fuels. There are different kinds of fuels that are being considered. And we have to certify aircraft engines for new fuels without having to go through the physical certification process as much as possible, because that's very expensive. So the idea is, can you build models that will tell you when flames will extinguish? And one of the requirements for certification is you take the engine to altitude. You have to, if it shuts off, you have to show that it can come back again in a short time, right? So high altitude engine relight, that's what it's called. And so you have to show that that's feasible. So what you do is you, the whole system, there's no flame in the system. There's a spark, typically a plasma torch or something that injects a spark. You have fuel and oxidizer coming in, but it's not that hot. It's relatively cold because the compressors have stopped turning, and so things are not being compressed or heated up and so on. And so the idea is, how does it spark and ignite the flame and form the flame? So the canonical flow here cannot be the count flow diffusion flame. It has no relevance to this problem. So the canonical flow here is are two systems. First, a homogeneous kernel, something that's a fuel-air mixture that's pre-mixed, the edge of which is igniting. That's the initial kernel ignition, just like an IC engine. And later, that transitions into a flamelet for which we can use something like what we saw before. So you have to combine canonical configurations here. So the experiment comes from Georgia Tech. This is part of their focus in this project. So they have a setup where there is a plate through which there's a torch or a plasma torch or igniter inside a hole. And the igniter sends an electric discharge. It ionizes the air, heats it up a lot, and then ejects this plume into the flow. The flow itself contains fuel and air coming to their mix, and they're coming in, not fully mixed, but somewhat mixed. They're coming in from the left like a jet in cross flow. This plume comes over, and it's supposed to interact with this mixture and then ignite it. Okay? Now what happens is, it doesn't always ignite. Okay? And this is something we have to learn to appreciate. So if you have a chaotic turbulent flow and you do something to the flow, there's no guarantee that each time it's going to give you the exact same result. Okay? So even in the experiments, they would run the experiment, they would ignite it, they would keep sending pulses. Some of those pulses will catch fire, other pulses will not catch fire. Okay? So there is an uncertainty in what's going to happen. We don't call it uncertainty, we call it variability. So you have the same system and it behaves differently at different times. Something you do not want in any engineered system, certainly not in an aircraft engine, right? You press a button, it should work. You don't want it to say, no, today I'm not going to work. Yeah? So this is a very dangerous thing. So what you're trying to figure out is reducing this variability. How can you reduce the variability? Now, there's a very simple way to reduce variability. That plasma torch that injects that high temperature fluid, you just put a gigantic plasma torch so that it just sends in enormous amount of hot fluid. If it does it, it will always burn, no questions asked. But the power required to make the discharge will be so high, you need additional backup for that. Right? So it's not going to work in regular place. So given an igniter, you want to understand what is the variability in whether this flame will catch on or not, okay? So which means you're going to pulse it many, many times. Only sometimes it's going to burn, okay? And you have to run this simulation many, many times to get that variability, okay? So not one single LES calculation, but maybe like hundreds of LES calculation, if not like thousands of them that you have to run to get that, what is the probability that ignition would happen, okay? So which means each calculation cannot be expensive, otherwise you're going to spend years doing these calculations. So our solution is to take this geometry, come up with that new manifold for this particular system, okay? And then we run multiple LES calculations. Each time, we change the inflow turbulence properties. So it's a different starting condition, different initial condition. We also change the strength of the pulse. So it may not, you deposit some energy. There's no guarantee that the arc that is discharged is going to spend all that energy into heating the fluid. There's some uncertainty there. So that variability needs to be accounted. So if you take into account both these variabilities, the pulse variability and the inflow variability, you can show that sometimes things will burn, sometimes it won't burn. So I'll show you this example here. I'll skip this for the moment. So there are two frames here. I don't know which one ignites and which one does not. They are identical simulations, no changes to models in either one of them. What has changed between the top and bottom is that the boundary conditions are a little bit different. So in one, it's a different realization of the turbulent flow, and also the pulse discharge is different. So when I run this, nothing happens. Oh, that's not good. Nothing actually happened. Okay. This is one of those days. I thought every movie that will not work actually worked, and the one I thought will work doesn't work. I can send you the working version of this. So what you'll find is that one of them catches fire and the other does not catch fire. So that's what happens in the videos. And we had to run maybe like 1,000 different LES calculations for this. And you can run all of them simultaneously because they don't depend on it. These are like samples of different inflow conditions. And because you use the model with heat loss or heat addition in this case, and strain effects and the right canonical flows, you are able to capture the same variability, probability of ignition that they see in the experiments also. So that's the main finding in this, okay? So I have a few more slides on this, but I want to stop for a while to sort of summarize what we have learned here. So one of the main things to figure out is that these flamelet approaches are very efficient. So once you figure out what is the manifold that you want to use, the variables that you're going to use, what is the mapping between Y and those manifold variables, the problem becomes extremely simple to solve. It's very efficient, and you can do everything from uncertainty quantification to predicting full-scale aircraft engines, things like this. Now, there are some disadvantages to this. First of all, you need to have the right canonical configuration. If you do not know where to get those mappings from, you may not be able to match experiments or make any specific statements about what the flame is going to look like. The other problem is that there's a tendency to add more and more variables to the table to make it more accurate, but that increases the cost quite a bit. Building the table itself now becomes complicated. So I just saw a paper with 7 variables, 7 manifold variables. Okay? So which means if you use 10 points in each dimension to construct the table, that'll be 10 power 7 points. So 10 million points. So those 10 million points typically comes from a large ensemble of canonical flow calculations. So now that simulation to generate the table might be more expensive than the actual simulation itself, right? So now it becomes pointless to do things like that. So all of this, you cannot take it to the full absurd extreme of adding more and more variables. You have to be careful about what needs to be added. But if you do that, then this method becomes a very reliable technique for simulating complex reacting flows. Okay, so I'll stop here. Any questions at all on this? Either it's very obvious or it's not. Nothing is clear. It's also excruciatingly hot here. I don't know if you guys noticed this. Yeah. My guess it's only a matter of time before the projector blows out. So, okay. So this is what we'll do. We are at 4 o'clock. I had a topic on transported PDF methods, which is not critical. So I don't want to belabor that point. It's only a way to solve the PDF directly if you don't want to use the manifold methods. It has a lot of other uses. Maybe if needed, we can come back to this. But I'll skip that part of it. So I want to take the break a little early. Yeah. So let's say we take another 10, 15 minutes. 4:20 we'll be back. And then we'll do one final run at this time. Not the whole thing, just this time. We have one more class tomorrow. So we'll do this. And there we want to look at dynamical systems, which is both interesting and terrifyingly complicated. So if you can get coffee or Coke, or not Coke in the sense, the one that you drink, right? So whatever, go get it and then come back soon.